It is a rather humbling thought that we know more about the distant edges of our solar system than we do about what lies just a few thousand miles beneath our own feet. The idea of a journey to the center of the Earth has captivated writers and dreamers for centuries, a grand adventure into a subterranean world of wonders. It is, however, an adventure we will almost certainly never take. The simple and rather inconvenient truth is that our planet does not want us there. Getting to the core would be the most profoundly difficult undertaking imaginable. The deepest hole ever drilled by humankind, the Kola super deep borehole in Russia, managed to penetrate a mere 7.5 miles into the Earth's crust. This sounds impressive, and in many ways it is, but it represents a paltry 0.2% of the total distance to the planet's center. At that modest depth, temperatures soared to a blistering 180 degrees Celsius, hot enough to bake rock and warp the toughest drill bits into uselessness. Go deeper still, and you reach the core, where temperatures are thought to rival the surface of the sun, reaching a staggering 6,000 degrees Celsius. Our most powerful tool for peering into the Earth's interior is something that, on the surface, seems entirely destructive: an earthquake. Every time the ground shudders and shakes, it sends out powerful vibrations called seismic waves. These waves are not just agents of chaos, they are messengers from the deep. Primary waves, or P waves, are compressional, much like sound waves. They can travel through both solids and liquids. Shear waves, or S waves, are more of a wiggle, moving up and down. Crucially, S waves cannot pass through liquids. They are stopped dead in their tracks. After a major earthquake, certain seismic monitoring stations on the other side of the planet would detect the P waves, but the S waves would be mysteriously absent. This created what is known as an S-wave shadow zone. There was only one logical explanation. Somewhere deep inside the Earth, there had to be a massive layer of liquid blocking the S-waves. Our journey begins, as all journeys must, at the surface. We live on the crust, the planet's outermost layer. In the grand scheme of things, the crust is almost comically thin, like the skin on an apple. Its thickness varies quite a bit, from as little as 3 miles under the oceans to as much as 40 miles under major mountain ranges like the Himalayas. The continental crust is much older, thicker, and less dense, composed largely of granite. Think of the continents as great ancient rafts of lighter rock floating upon the denser material below. Beneath this familiar crust lies the Mohorovičić discontinuity, mercifully called the Moho. It was discovered in 1909 by Croatian seismologist Andrija Mohorovičić. He noticed that seismic waves from a nearby earthquake suddenly accelerated at a certain depth. This sudden change marked a clear boundary between the crust above and the entirely different layer below, the mantle. If you cross the Moho, you find yourself in the mantle, a colossal layer of silicate rock that extends nearly 1,800 miles deep. The mantle is, by a very wide margin, the biggest part of our planet. It is a place of unimaginable heat and pressure. While we often think of it as a liquid, like a subterranean ocean of magma, that is not quite right. For the most part, the mantle is a solid. However, it is a very special kind of solid. Under the extreme conditions found there, the rock becomes ductile, meaning it can deform and flow very slowly over geological timescales. The mantle is heated from below by the planet's core and cools as it gets closer to the crust. This creates enormous, sluggishly churning loops known as convection currents. These currents are the great planetary engine, the driving force behind much of the geological activity we experience on the surface. The entire process is incredibly slow, with the rock moving at about the same speed your fingernails grow. But over millions of years, this movement can rearrange entire continents. Without the mantle's slow-motion dance, our planet's surface would be a very different and likely much less interesting place. Descending beyond the vast flowing mantle, we arrive at the most dramatic boundary of all. At a depth of about 1,800 miles, we hit the outer core. The rock of the mantle gives way to a searingly hot ocean of molten metal, primarily iron and nickel. The temperatures here are extraordinary, estimated to be between 4,000 and 5,000 degrees Celsius. How can we be so sure it is iron and nickel? First, we know the Earth's overall density by measuring its gravitational pull. Since the crust and mantle are made of relatively light silicate rocks, something much denser must be lurking in the center. Iron and nickel are not only very dense, but they are also cosmically abundant throughout our solar system, found in meteorites that are thought to be the leftover building blocks of planets. This swirling liquid metal ocean is not just sitting there idly. Heat flowing from the even hotter inner core drives turbulent, churning motions within the molten iron. Because iron is a conductor of electricity, this movement of a conductive fluid creates something truly remarkable, a geodynamo. As the liquid iron flows and swirls, it generates powerful electrical currents that produce Earth's magnetic field. This magnetic field is profoundly important. It acts as an invisible shield, deflecting the most harmful charged particles that stream from the sun in what is known as the solar wind. Without this protection, the solar wind would strip away our atmosphere over time, leaving the surface exposed to deadly radiation. Life as we know it simply could not exist. At the very center of our planet, within the turbulent ocean of the liquid outer core, lies the final destination of our journey, the inner core. At a depth of about 3,200 miles, something amazing happens. Despite the temperature being even hotter than the outer core, reaching an astonishing 6,000 degrees Celsius, as hot as the sun's surface, the metal here is solid. This seems completely counterintuitive. The answer lies in one word: pressure. Here, the weight of the entire planet pressing down creates a pressure that is almost beyond imagination, over 3.6 million times the pressure at the surface. This immense pressure forces the atoms of iron and nickel so tightly together that they can no longer move around as a liquid. Instead, they are locked into a fixed crystalline structure. One of the most fascinating discoveries is that the inner core seems to be rotating, ever so slightly, faster than the rest of the planet. It appears to be slowly spinning within its liquid shell, gaining on the surface by a fraction of a degree each year. Perhaps the most profound thing about the inner core is that it is growing. As the Earth gradually cools over billions of years, more of the liquid outer core slowly crystallizes and freezes onto the surface of the solid inner core. Our imaginary voyage to the center of the Earth ends here, at a solid iron ball hotter than the surface of the sun. We have traveled through a brittle crust, a flowing mantle, a liquid metal ocean, and finally to a solid, crystalline heart. It is a world utterly alien to our own, governed by pressures and temperatures we can barely conceive of. Yet, the processes unfolding in these hidden depths are not remote and disconnected from our daily lives. Every mountain range that scrapes the sky was pushed up by the slow, inexorable collision of tectonic plates, driven by the convection currents in the mantle. Every volcanic eruption that builds new land is a direct manifestation of heat and molten rock escaping from that same planetary engine. The life-giving magnetic shield, which protects our atmosphere from being scoured away by the solar wind and allows complex life to thrive, is a gift from the turbulent liquid outer core. These are not separate, isolated facts. They are parts of an exquisitely interconnected system. What happens in the core affects the mantle, which affects the crust, which in turn dictates the conditions for life on the surface. So while we may never physically make the journey, the exploration of our planet's interior continues. With every earthquake, we learn a little more. With every computer simulation, our picture becomes a little clearer. It inspires a certain kind of awe to realize that our stable, comfortable world is the surface expression of such immense and ancient forces. And there is still so much left to discover, so many echoes from the deep still waiting to be heard.